Okay, good morning, everyone. So we have been talking about addition of angular momenta. And so today we're going to be doing the general case of two completely arbitrary angular momentum operators that we're going to call J1 and J2. And so the idea is we have two possible complete sets of commuting observables that are nice. Both of them include J1 squared and J2 squared, but one of them we use J1z and J2z. This is called the product basis. And the other one, we also use J1 squared, J2 squared, but we use the total J squared, and we use the total JZ component. And that's the total basis, really the total angular momentum basis. So the way we write this schematically is that we say we're taking the product of two angular momenta J1 and J2. We can write that as a sum of the total angular momentum eigenvalues, with the highest one being J1, J2, J1 plus J2, and then decreasing by 1 unit until we get to the lowest possible one, which is the difference in J1 and J2 in absolute value. So this is the product basis. This is the total angular momentum basis. And so let's just count states to make sure we understand what's going on here. So in the product basis, we have states that we can write as M1, M2, and we put a colon between them to represent that we're in the product basis. Okay, and the total number of such states is just going to be 2j plus 1, or 2j1 plus 1. That's the total number of M1s that there can be, times 2j2 plus M1 plus 1. Whereas if we instead did things in the total basis, then we would have states that look like this. First of all, there's J1 plus J2 with all of its possible values of M. And the number of those is 2 times J1 plus J2 plus 1. So that's how many states there are in that part, just the J1 plus J2 total angular momentum. And then there's J1 plus J2 minus 1 with all of its possible values of M. That has 2 times J1 plus J2 minus 1 plus 1 states. Okay, and then we keep doing that until we get to the states with the absolute value of J1 minus J2. And that has 2 times J1 minus J2 in absolute value plus 1 states. One easy way to do it is just assume that J1 is larger than J2. Then I wouldn't actually need the absolute value that I'm writing here. Okay, and then if you add those all up, so the total of adding those up is 2j1 plus 1 times 2j2 plus 1. You can check. And so that agrees with the total number of basis states in the product basis. So the fact that they agree is a good sign. It means that in both cases, we have a basis for the total state space. Okay, so if we have two different bases, then we can relate them by completeness. Right, and completeness says if I take any state, for example, Jm, I can expand it in terms of the product basis. So I can do a sum over all possible M1s, which go from minus J1 up to J1, and over all possible M2s, which go from minus J2 up to J2, of the states labeled M1, M2. Those are product basis states with coefficients that are just given by this, M1, M2, inner product with Jm. Okay, so that's here I've just rewritten the identity operator as a sum over all the possible states that there are in this orthonormal basis. And therefore, these are some coefficients, which are known as Clebsch-Gordon coefficients. Okay, and these are for J1 and J2. So notice the notation that we've been using, or that we've written in this, omits the J1 and J2. That's just supposed to be understood based on whatever context we have for this equation. So if I restore that J1 and J2 so that I can use it in some other context, then the Clebsch-Gordon coefficients can also be written in the following way. And this is sort of a more standard way to write it if you're making a big table of them. You would say J1, J2, product basis M1, M2, inner product with J1, J2, J and M. Those are your Clebsch-Gordon coefficients. Okay, and then you can look these up in tables. But one thing I'd like to point out is just that there are different conventions for these tables. So you have to be a little bit careful, because if you're using some table, it may or may not agree with the conventions I use, and it may or may not agree with some other book. So different conventions. Okay, so we have this completeness relation involving Clebsch-Gordon coefficients, but there's another way of doing completeness, which is we can say, so completeness also says that instead of writing the total angular momentum states as linear combinations of the product states, we could write the product states, for example, M1, M2, as a sum over all possible total angular momentum states. So now we're going to sum J from the smallest possible value it can have, which is the absolute value of M1 minus M2, up to the largest value it can have, which is M1 plus M2. And for each of those J's, we sum M from the smallest value it can have, which is minus J, up to the largest value it can have, which is J. Okay, so we're writing a linear combination of total angular momentum states. And the things that will go here are Jm, M1, M2. Right, so once again, I've just written the identity operator in a fancy way. And then as a linear combination of these states, I have these coefficients here. But those are just the complex conjugates of the Clebsch-Gordon coefficients. So complex conjugates of the Clebsch-Gordons. Except that we can and will choose them real. You don't have to do this, but essentially all books do. All books, even if they don't use the same conventions that I'm using, they will at least choose them to be real. And so if we choose them real, they're not actually the complex conjugates. They're again the Clebsch-Gordon coefficients. So we can ignore the fact that technically these are the complex conjugates as symbols of those, but they're all real anyway. Okay. So we've already done basically the work of finding the complex conjugate, the Clebsch-Gordon coefficients for some special cases. So we have found so far the following special cases. First of all, we did the inner product, or we did the direct product of two spin 1/2, and that gives total spin 1 and total spin 0. And what we found was, I'm going to write in this column the total angular momentum states as linear combinations of the product states, the product basis states. So we had total spin 1, m component 1, total spin 1, m component -1, total spin 1, m component 0. And if the total spin is 0, then the only m component you can have is 0. Okay, and this is in the product basis. The first one is 1/2, 1/2. In other words, both spins have to be pointing in the positive z direction in order to get them to line up to give 1. We also wrote this state. We have different ways of writing everything. And so we also wrote this as up arrow, up arrow. That just corresponds to +1/2, +1/2 for the m components. Okay, and similarly, 1 - 1 in the product basis is 1/2 -1/2, sorry, -1/2 -1/2, which would be also known as down arrow, down arrow. And the 1, 0 is 1 over square root of 2, 1/2 -1/2 plus -1/2 1/2. Whereas 0, 0 is the orthogonal linear combination of those two product basis kets. So the same thing, but with a minus sign. So we had worked this out by finding how to write one state in terms of another state. But now if we want, we can go ahead and look back at this equation. And we see that basically this information is the same as the Clebsch-Gordon coefficients. So we can take this and say the non-zero Clebsch-Gordon coefficients are the following. Okay, and I'm going to write this in the form where we include the J1, J2 information. So 1/2, 1/2 is J1, J2, and then 1/2, 1/2 for the product basis m's. Inner product with 1/2, 1/2, 1, 1 is just equal to 1. Okay, that's the information contained in this statement. Okay, and then similarly, and I'm going to not write the 1/2, 1/2s, but you could. So I'm just going to leave a space for them there. 1/2 -1/2 1, 0 is equal to 1 over the square root of 2. Okay, and so that's the information from here. And we can do minus 1/2, 1/2, 1, 0 is also 1/√2. That's the information from here. Okay, and then we can do minus 1/2, 1/2, 0, 0. That's equal to minus 1/2. Okay, from here. And 1/2 minus 1/2, 0, 0 is plus 1/2. That's from here. And then finally, there's the fact that minus 1/2 minus 1/2, 1 minus 1 is 1. Okay, and that comes from here. So all of this information that we worked out in terms of writing states in terms of each other's can be summarized in these Clebsch-Gordon coefficients. All right, any questions on this so far? All right, so the other example that we had done is we had done the case where one of the angular momenta is an orbital where L is an integer, and we're taking the direct product with the spin, which is 1/2. Okay, and that's always equal to the following direct sum in the total angular momentum basis, where it's L plus 1/2 and L minus 1/2. And then if we say the total and the product basis, again, I'm going to write them in columns. So if we have L plus 1/2 m, that worked out to be the following linear combination: square root of L minus m plus 1/2 over 2L plus 1, m plus 1/2 minus 1/2, plus a different square root, L plus m plus 1/2 over 2L plus 1, m minus 1/2, 1/2. Okay, so in both cases, notice the total z component of the angular momentum, of the total angular momentum, is m, because here we have m plus 1/2 and minus 1/2, and here we have m minus 1/2 and 1/2, and that adds up to m in both cases. Okay, and then there's these states that have total angular momentum L minus 1/2. And one way to get them is to require that they be orthogonal to the one on the line above. In any case, when you work it out, you get this. So it's a linear combination of the same two states, but with different coefficients. So this is a minus. Okay, but the same state appears here. Okay, and now if you take the inner product of these two to check that they're orthonormal, you basically have this square root times that square root minus the same products of square roots, and so that's going to give 0. So they're indeed orthogonal. And now from these equations, you can read off the non-zero Clebsch-Gordon coefficients. This is for L times 1/2. And so you're just reading off those coefficients. So for example, you have m plus 1/2 minus 1/2 L plus 1/2 m is the square root of L minus m plus 1/2 over 2L plus 1. Okay, and etc. You can read off the others in the same way. Okay, now having gotten the Clebsch-Gordon coefficients, now we can use the trick to apply this to get the product basis as linear combinations of the total basis, which is sort of the inverse problem of what we've already done. So as linear combinations of the total basis. And that's just a matter of using the Clebsch-Gordon coefficients in the equation. Let's go back up here in this equation. And so if you apply that in this situation, you get, for example, that m plus 1/2 minus 1/2 is equal to square root of L minus m plus 1/2 over 2L plus 1. L plus 1/2. Now on the right side, I'm writing in the total basis. And the coefficients that go here are, again, these square roots. Okay, so that's one of them. And another way of writing that is we can say that let's call m sub L equal to m plus 1/2. The reason for doing that is because this first entry in the product basis is really the m for the angular momentum L. So we're calling it m sub L. It's equal to m plus 1/2, where this m is the total m, the m for the total angular momentum. So if we just do that rewriting, then we get m sub L minus 1/2 equals, and now I'm just plugging this into the coefficients. I get L minus m sub L plus 1 over 2L plus 1, L plus 1/2, m sub L minus 1/2. Okay, and then the other square root looks like this. L plus m sub L over 2L plus 1, L minus 1/2, m sub L minus 1/2. Okay, so again, this equation that I've written here is really just rewriting this equation, but with a notation where I've just changed what I'm calling the first entry. I'm calling it m sub L, which makes sense if I'm thinking of this as the z component of the angular momentum L. Okay, and then similarly, you can check that, for example, the state m sub L plus 1/2 is equal to this square root times that state minus L minus m sub L over 2L plus 1, L minus 1/2, m sub L plus 1/2. Okay, so one thing to notice here is that all the Clebsch-Gordon coefficients are always real in our convention, but they're not always positive. So all Clebsch-Gordons real, but not all positive. So in general, there's some of them that are chosen to be real and positive. And we talked about that as the Condon-Shortley convention. And in a few minutes, I'll give you the Condon-Shortley convention in general, how it works in general. But unfortunately, you can't choose them all to be positive. Okay, any questions on that before we go directly into the most general case? All right, so let's understand how to do the Clebsch-Gordons for the most general case. And so I'm going to assume, without loss of generality, that J1 is at least as big as J2. If that's not true, then you just interchange the roles of J1 and J2. And now what we're going to do in terms of writing the product basis in terms of the total basis is we're going to start with the highest JM state. Okay, and the highest one that can be is when J is equal to M is equal to the largest thing it can be, which is J1 plus J2. So the thing about that state is it's unique. There's only one way to choose J and M such that they're the maximum. And so we can immediately write down that J1 plus J2, J1 plus J2, those are really J and M in the total angular momentum basis. That must be equal to, in the product basis, J1, J2. Okay, and that's just because this is unique in the sense that the two angular momenta in the z direction are maximally lined up. So you have the maximum possible J sub z. Okay, and now the strategy is to keep acting with J minus. So we act with J minus, which is defined to be J1 minus plus J2 minus. And so in the first step, we act with it on the left side. And we have a formula that tells us what J minus does to angular momentum eigenstates. It's got a h bar, and it's got this square root. And so we just have to plug in the values, which are J1 plus J2 plus J1 plus J2 times J1 plus J2 minus J1 minus J2 plus 1. Okay, times the state that we get by lowering the M value by 1. So J1 plus J2, J1 plus J2 minus 1. Now, the nice thing is all of this stuff just goes to 0. And so this whole factor is just 1. And so the whole thing is just h bar square root of 2 J1 plus J2 times the state where we've lowered the M value by 1 unit. Okay, so that's also equal to J1 minus plus J2 minus, acting on the right-hand side of the boxed equation, which is J1, J2. Okay, so the idea is we're going to compute this in a slightly different way and see that the two, and make the two agree. So this is equal to h bar square root J1 plus J1, J1 minus J1 plus 1 This is all using our general formula for what J minus does. Okay, that's on the J1 basis. Notice the J1 minus only acts on the first slot. So it only lowers J1, it just completely ignores J2. So on your homework, there's a similar situation where you're dealing with a spin, which can be a spin 1 or a spin 2, and the spin 1 operator only acts on the first slot of the product basis, and the spin 2 only acts on the second slot. So it's the same idea here. And then the other term looks exactly the same, except with J1 replaced by J2 everywhere. Okay, and now we're lowering the spin or the angular momentum component that goes in the second slot. So now J2 gets lowered by 1. Okay, and so now we can simplify this. This is once again 1, and this is 1. And so the whole thing is h bar square root of 2 J1, J1 minus 1 J2, plus h bar square root of 2 J2, J1, J2 minus 1. Okay, so the idea is we've computed the same thing 2 different ways, and therefore we can say that this has to be equal to this. Okay, and so now we just solve by dividing by this coefficient in front. And so the result that we get is J1 plus J2, J1 plus J2 minus 1. This is again in the total angular momentum basis, is equal to 1 over the square root of J1 plus J2 times square root of J1, J1 minus 1 J2, plus the square root of J2, J1, these should be colons actually, because this is in the product basis. So this should say J1 colon J2 minus 1. Okay, and this is an equation that we've previously derived in special cases. So we have previously derived this for the special cases J1 equals J2 equals 1/2, and the special case J1 equals L and J2 equals 1/2. Okay, and now you just keep doing this. This is our new boxed equation, let's say. And you act with J minus again. Okay, and so you write J minus in 2 different ways. That way you have 2 expressions that have to be equal to each other. And then you can solve for the total angular momentum basis states. And you eventually get to the state that has J1 plus J2 minus J1 plus J2. Okay, and if everything has gone correctly as a check, this has to be equal to minus J1 minus J2 in the product basis. If it turns out not to be true, then something went wrong, because this has to be true because it's unique again. It's the minimum possible J sub Z. Okay, and so this is an opportunity for a check. And in fact, we could have done everything the opposite way. We could have started with this equation And then instead of acting with J minus, we could have acted with J plus. That would have just given a different set of square roots, but otherwise it would have all been the same. And we keep acting with J plus, and we would eventually have ended up back with this equation as our check. Either way will work. It's sort of more traditional to start with the highest one and go to the lowest one, but there's no real reason why that has to be true. So now if we stare at this, we realize that we've got all the states that have total angular momentum J1 plus J2. There's these ones, and then there's the ones in between. And there was this one back up here. Okay, and so we can say that we are done with total angular momentum J equals J1 plus J2. We've found all the states in terms of the product basis for those states. So now we need to work on the next lowest value, which are the states or the kets with J equals J1 plus J2 minus 1. Okay, and so we're going to actually be repeating what we've done in the special cases, but now just with more generality. So we start with the maximum value that M can have. And the largest possible value M can have is J1 plus J2 minus 1, because that's what J is. And so what we can say is that state, or that ket, should be equal to, now it's not unique because there are two different kets that you can write in the product basis that have that same value of M, and here they are. So I'm going to write a coefficient A times J1, J2 minus 1, and another coefficient B times J1 minus 1, J2. Okay, but the state on the left-hand side is not degenerate. How do we know that? We know that because we have a complete set of commuting observables. So is not degenerate. J1 squared, J2 squared, J squared, and Jz are a complete set of commuting observables. Okay, and that means that state is unique. And that means it must be possible to solve uniquely for A and B up to a global phase. You can never actually solve for the total phase in front of a ket because it's not observable, as we saw in the postulates of quantum mechanics, but we can at least solve for A in terms of B and then use orthonormality. So in other words, what we do is we use the following facts. We use the fact that it's orthonormal to the state that we've already found that has the different value of J, but the same value of M. Okay, and we use the fact that it has norm 1, which tells us that A squared plus B squared in absolute value has to equal 1. Okay, so we've got two equations in two unknowns, but they're complex. And so the other thing we use is the Condon-Shortley convention. So the Condon-Shortley convention says that A you choose to be positive. So you do that. Remember, we assumed that J1 was greater than or equal to J2. If J1 happens to be equal to J2, then they're the same. So you just pick one of them. It doesn't matter which. Okay, so those pieces of information are going to give you A and B. You can solve for them both. Okay, and so now you've determined, in general, you've determined what this state is. Okay, and so once you do that, you can apply J minus again to get all the other states with that same value of J. So those states are the following form: J1 plus J2 minus 1, M. Okay, and then the last one is going to have the lowest value of M, which is minus J1 plus J2 minus 1. Okay, so now you repeat this. Now we need states that have even lower values of J. The next lowest value of J is J1 plus J2 minus 2. Okay, and so again, you start with the maximum value. The maximum value for M is the same as J. So J1 plus J2 minus 2. All right, and so let's write down what's the most general possibility that that state could be. It's going to be J1 plus J2 minus 2. J1 plus J2 minus 2. Okay, now there are 3 states in the product basis that could give this same value of M. So here they are. I'm going to reuse the coefficient A, J1, J2 minus 2. And the other things are J1 minus 1, J2 minus 1, and J1 minus 2, J2. So unfortunately, we now have 3 unknown coefficients, A, B, and C, that we have to solve for. So how are we going to solve for them? We're going to fix A, B, and C by the following conditions. First of all, they all have to be, these states have to be orthogonal to the states that we've already found with different eigenvalues for the complete set of commuting observables. Okay, so they have to be orthogonal to J1 plus J2, J1 plus J2 minus 2, and J1 plus J2, J1 plus J2, sorry, J1 plus J2 minus 1, J1 plus J2 minus 2. Okay, so these are states that we've already found, and they have a different value of J, namely J1 plus J2 and J1 plus J2 minus 1 instead of J1 plus J2 minus 2. And so these 2 states both must be orthogonal to that, and that gives you 2 equations. So far that'll be 2 equations. Then there's the equation that from the norm. So if we want this to have norm 1, then A squared plus B squared plus C squared has to equal 1. That's 3 equations in 3 unknowns, but they're complex, so we have to worry about the phase. And now the Condon-Shortley convention is again that A is real and greater than 0. Okay, so that fixes everything there is to know about A, B, and C. And so once again, you can solve for them. All right, so now the general scheme is you just keep doing this. You act with J minus until you get 0. Then you use orthonormality to get the next state with the next lowest value of J. And eventually, you will get the state J1 minus J2. I guess I don't need to put those in absolute value since I claimed that J1 was greater than or equal to J2. So I can just write it as J1 minus J2 M. So you get all those states. So it's sort of a complicated process, but it's an algorithm, and you can draw a picture of the general scheme for doing this computation to find the total basis kets in terms of the product basis kets, or as linear combinations of the product basis kets. Okay, and this is all for some J1, J2. So summarizing what we did, we start with the largest value of J, which is J1 plus J2. Then we have a unique ket, J1 plus J2, J1 plus J2. We act with J minus. That gives us the next ket lower in M. We keep acting with J minus to keep getting kets with lower values. Okay, we keep acting with J minus. Eventually we get J1 plus J2 minus J1 minus J2. That ket should be a check. Okay, and then we start with this one. We require orthonormality. And we get J1 plus J2 minus 1, J1 plus J2 minus 1. Then we go down acting with J minus each time until we get to J1 plus J2 minus 1 minus J1 minus J2 plus 1. Okay, and then the second one here, we again use orthonormality. Okay, and we keep going this way until we finally get to J1. So it's J1 minus J2, J1 minus J2, and then we act with J minus however many times we need to until we get the last state. Okay, and so in each of these, the last state in each column is a check, because those should be equal to those should be unique in the sense that they're going to be the same as the things in the top of each column, but with some minus sign changes in general. Okay, so that's the general idea of how these things work. As I said, you can actually look these things up in tables rather than going through the whole complicated procedure every time, but it's of course important to know what's going into the determination of the tables. All right, any questions on that? We'll be talking a little bit more. I'll be sort of reviewing this again on the last day of class, which is on Friday. No questions? Okay, so again, Friday's class is going to be back in person, face-to-face in the usual room. Also, I just sent out an email because somebody pointed out that the schedule that I had for the final exam was based on an old class meeting time, which we no longer have. And therefore, according to the university's policy, the final is on Wednesday, not Monday, which is good because you get 2 extra days to study. but it's bad because the university says we have to do it at 8 a.m., which is not my choice. Okay, and then the homework 10, because you have 2 extra days to study for the final, I'm going to make the homework 10 due Saturday at midnight. I had previously said that it would be Friday at midnight, but so now you get an extra day for that if you want. If you have to take that time to study for other exams and other classes, that's also a possibility. Okay, so this changed from Monday to Wednesday, and unfortunately at 8 a.m. All right, any questions? All right, if not, then I will see you on Friday in person at 9 o'clock. All right, have a good day.
Thank you.